Hi, this is week 3 of chemistry, and we're going to go ahead and talk about the Big Bang Theory. Along with the Big Bang Theory, we're also going to talk about the formation of atoms, where do atoms come from, and electromagnetic radiation as well. Alright, so let's get started. The objective for this lesson is for students to understand what is the Big Bang Theory and the supporting evidence, as well as students need to know where atoms come from. And lastly, we're going to talk about electromagnetic radiation and how it is used to collect data on stars. Alright, so let's get started. First of all, Big Bang Theory states the following. About 14 billion years ago, the universe was concentrated in a very, very small place. That's called a singularity. Everything in the universe, every star, every planet, everything. And this, how big is it? It's considered to be infinitely small and had infinite amount of gravity inside of it. The singularity also contained not just all the matter in the universe, but also all the heat in the universe, as well as all the space-time in the universe. So if you were to ask a question, so how long was it there? And we cannot give you an answer for that. Science doesn't have an answer for that, because if time and space was in the singularity, and if you're standing outside looking at it, there is no time. So it could have been there an instant, could have been there an eternity. So there's no real answer to how long it was there. And it is so incredibly hot that even all the rules we have for physics, they completely break down. They don't work in the singularity. Now, at some point, for some unknown reason, the singularity became unstable and began to expand very quickly. That is referred to as the Big Bang Theory, that expansion of that singularity in one little spot, just all of a sudden expanding quickly. So that's the Big Bang Theory. Now, in this diagram, what you're going to see is just in the first few seconds, you're going to go ahead and get the expansion begins, and you start getting protons, and those protons are going to go ahead and get together to form atoms, very, very small atoms, such as mainly hydrogen and some helium. Now, that will take about a minute and a half. From there on, that hydrogen is going to go ahead and gather into clouds, and because every single particle with mass has gravity, they're going to pull themselves together in a cloud, and eventually that's going to form a star. 500 million years later, that is the earliest known galaxy was formed. And 4 billion years after the Big Bang, that's when you have the most amount of stars. Now, the Big Bang Theory is supported by the movement of galaxies. Now, picture this. If you could see a galaxy moving and track where it's going, if you see it go across, then you can also more or less figure out where it came from, the direction that it came from. And if you know its velocity, how fast it's going, then you can go ahead and work it backwards to figure out where it came from. And what they found out is that all the galaxies came from one single spot. And that's how the Big Bang Theory got supported. That pretty much if you see where every galaxy started moving from, it's all in the same spot. Next, we're going to go ahead and talk about the formation of elements. And I don't know if you've ever taken the time to think about, where do all the atoms that make me come from, or make you? Where do all of them come from? And the journey that they took to get to where you're at right now, it's an amazing journey that took billions of years. So let's go ahead and get started. It all began soon after the Big Bang. You have very large clouds of hydrogen, like this picture you see taken by the Hubble telescope. And all of these atoms have gravity. Even though they're tiny, it is gravity, and they're able to pull each other with that gravity towards each other, so they stick to each other. And that's going to continue once you have two of them that are side by side. Now that you have more gravity because you have double the mass, and it's going to pull other atoms together, and that's what keeps the cloud together, that little gravity. And these atoms are going to go ahead and continue to cluster together. And what's going to happen next is that these large clouds of hydrogen, they're going to get very massive once you have a lot of hydrogen atoms, and they're going to go ahead and their gravity pushes them together, and pushes them towards each other until fusion happens. And fusion is when two smaller atoms get together to make a bigger atom. And now notice this one is one proton and one neutron, one proton and two neutrons, and what they will create is this one with two protons and two neutrons, so it gets larger. A neutron was released along the way, but also a lot of energy gets released along the way. That is nuclear fusion, of putting two atoms together to make one bigger one, and that is what creates a lot of energy. Now, this atom that's created, it's now helium. So you got two hydrogen atoms, the gravity pushes them together to make helium, and so you have a bigger atom. And that process continues in the clouds, and it starts creating now bigger atoms, so therefore more gravity pulls that cloud in closer, and at some point when you have enough energy, that is the birth of a star. That's how it begins. And those stars have a lot of hydrogen. That's pretty much the essential first atom. Then it'll start making a lot of helium. Along the way, that star is going to continue making more elements. It gets one element here, another element right there, and the gravity pushes them, and again they fuse into each other, and that continues, and you start making more of the heavier elements. And as the star goes along and billions of years pass, eventually it's going to run out of hydrogen, but it's okay, it's got a lot of helium, and it's going to get that helium and smash it together to make bigger atoms like beryllium and carbon and so on. And this process will continue over billions of years until you eventually get to iron. And a regular star will go ahead and make all the way up to iron, and that's usually about as high as it can go in the periodic table, which is element number 26 in the periodic table. At this point, once it has a lot of iron, the star becomes unstable and begins to die, and when it dies, it explodes. And an explosion of a star is referred to as a supernova. Alright, once the star consumes all of its fuel, once all the fuel is gone, it will explode. Then you have your supernova. And that supernova explosion creates a massive shockwave that it's able to get those elements that were there and again smash them into each other to create even bigger elements. So remember what I said, the star only makes up to iron. Once it dies and it explodes, those heavier elements are made by that explosion. Now this explosion of supernova is a massive explosion. A supernova explosion can produce as much energy as that produced by our sun over its whole lifespan. The whole time that it's burning, all that energy that it produces, a supernova can produce the same amount of energy. And it is as bright as a galaxy. So here you have a star, this is the before, and this is a star going supernova. This is other images captured by the Hubble telescope. So it's a massive, massive explosion. So in this diagram, you see which elements are created in the Big Bang. It's mainly hydrogen and helium. And then the other ones after that here in this light yellow, those are created by the larger stars. And you can see them right here. All of these guys are created by the largest stars. Some small stars will create smaller elements. But in blue, those bigger elements, those heavier elements, those are only created by a supernova explosion. Eventually, pieces of the star fly off in every direction. Again, they have gravity, so they're going to cluster together. And again, that's going to create planets along the way and other stars along the way as well. So our planet was created by chunks of a star that died and exploded in a process that took billions of years. And if you think about that for a second, that means every atom that makes you, at some point, was created inside of a star, took billions of years, exploded, got scattered throughout the whole universe. They eventually came together once more and are now you. So it's an amazing journey that every single atom that makes you takes to be part of who you are. So it's a very amazing journey and truly, truly awe-inspiring. Alright, now we're going to go ahead and move to electromagnetic radiation, which is, think of it as light. Now, definition for electromagnetic radiation is the flow of energy at the speed of light through space or through a medium, like air or water is a medium, in the form of either electric or magnetic fields such as radio waves, visible light, which is what you can see, and gamma rays. In this diagram, which is a little bit bigger here, you can see this is all types of electromagnetic radiation, which includes gamma rays, X-rays, UV light, infrared, microwaves, AM, FM radio waves, and long radio waves, long range radio. This tiny band right there, That's referred to as the visible spectrum. That's visible light, light that your eyes could see. So there's a lot more light out there. All of this on the left, all of this on the right, that your eyes cannot see. All we could see is this very small band right here. Alright, so that is visible light. Now exactly how does that work as far as color? How come some atoms give you one color, other atoms give you another color? It has to do with the movement of electrons within the atom. Here in this atom, you have the electrons here in yellow going around. When energy hits it, the electron absorbs that energy and it goes from this energy level or orbit that it's traveling in, and it jumps to a higher energy level. And it's as it spins around the center of the atom, the nucleus. Now it's going to hold on to that energy for a while. Eventually it's going to let it go. When it lets it go, it goes back down. So one more time, starts at a lower orbit and absorbs energy, jumps up. When it's at a higher energy, it's referred to as it's in an excited state. When it releases the energy, it releases it as light. Now depending on how far it moves, then that's how much energy is released. So the movement of the electron is going to go ahead and, if this is small distance, it gives you a very small amount of energy. If it's a larger distance, it gives you more energy. And the amount of energy it has a different wavelength, and that's what creates a color. Alright, so here you have it. Smaller jump from the first energy level to the second. That gives you a small amount of energy. Red light has very little energy. But a much bigger jump from the first energy level to the fourth one, that's going to give you blue light. Blue light has more energy than red light. So electrons in an excited state will move from their current energy level to a higher energy level. Eventually the electron will release that light, that energy, and it will release light, and it will go back down to its lower energy level. So some atoms will only move here, other ones there, and that's what gives you different color lights. So the photon of light emitted by the electron has a specific amount of energy that can be used to identify which element is there. So here we have some flames, and they're all different colors, and the different colors in the flames can tell you exactly what is burning. So that's our first clue. How is an astronomer able to look at a star and tell you, oh, well, no, I know what elements are there? And the answer is by the color of the light. Alright, and very much the same way, if you've ever seen a fireworks show, and they have a firework explodes and it might be green and the next one's blue and the next one's white, and you might be wondering, how do they achieve the different color flames? And the answer is different metals will burn in giving you different colors. So each one of those elements, as you can see in this picture, will give you a different color. So by just using the color, you can identify them. Now, they don't just look at the color with their naked eye. What they will do is they'll get the color and run it through a prism, and the prism will spread out that light into the spectral lines. So you see right here. So for example, hydrogen will create these two blue lines here, a teal there and a red-orange color right there. Helium has different spectral lines. There's sodium and there's mercury. Each element has their own spectral lines. None of them match each other. So by looking at the light, you can identify, oh, that light is mainly hydrogen. By running it through a prism, spreading it out, looking at the spectral lines, and here's a better picture of that. So you can identify it. Oh, that one is helium. A young star will have a lot of hydrogen, and that's how they're able to figure it out. Once you start seeing iron, that's one of the heavier elements that the star produces. You say, well, that's a very old star. It's probably on its way to going into a supernova explosion. So using the light of the stars, running them through a prism and comparing what elements are there, you can figure out more or less the age of the star. On top of that, you can figure out how far a star is using this setup. So the sun's right here. Here's planet Earth. If you go ahead and look through a telescope to where a star is, figure out the angle at which you're at, then wait about 6 months, you're on the other side of the sun. Go ahead and measure where the star is at. You can get the angle. Notice that it makes a right triangle. And using simple algebra, some sine, cosine, and tangent, you can go ahead and figure out this distance from our star, the sun, to that star that you're trying to measure. Alright, so that is other information that astronomers can gather just by the light, where is it, and figure out its distance. So now you can figure out how far it is and how old it is by looking at the light as well. Moreover, you can use the Doppler effect to figure out if that star's moving towards us or away from us. The Doppler effect is a shift on how the light looks. So for example, let's say that neither Earth nor the galaxy in this case is moving. So we have, you see that black line right there in the middle of the green? Alright, so we have a green light coming in. If the galaxy is moving away from us, what that will do is it will stretch the light so it has a longer wavelength. It's going to go ahead and stretch it, and that will move that black line here slightly over. Let me go to a bigger picture. Now it's going to move slightly over towards the red side. So if the galaxy or the star is moving away from us, you see it's no longer green, now it's yellow. So it moves closer to the red side. So it's referred to as a red shift. If a star is red shifting, it is moving away from us. But if the galaxy is moving towards us, that's going to compress the wavelength, giving you smaller wavelengths. And that light, rather than being that light green, now it's going to give you a dark green. Notice how it was here, now it's here. So it moved towards the blue side, so you refer to that as a blue shift. That means that the galaxy is moving towards us. So by using the light, you can identify what elements are there. You can identify how far away it is. And lastly, you can identify if that starts moving towards us or away from us. Alright, so that is electromagnetic radiation, and that concludes this lesson on the Big Bang Theory. Thank you so much for watching.